Swayam Prabha. Digital India. Educated India.
Hello. So, we continue our discussion on linear autonomous second order systems. In the previous lecture, we had a look into various phase portraits which are possible under different conditions, all of which satisfied a similar equation which is given by dx by dt is equal to a x, where x is the dynamical vector and a is the matrix. Today, we will take an example of a physical system. So, the example that we have today is a spring mass system. Now, whenever a spring comes into our mind, what do we think? We think about something which oscillates, right. So, we ask ourselves a question, can we have a spring which is not at equilibrium and still tries to come to equilibrium without oscillation. So, let me repeat, if I give a disturbance to a spring, I expect it to oscillate. Now, the question is, can I have a spring which when given a displacement in its mass would like to come back, would have a tendency to come back to the equilibrium, but without oscillations. Well, in fact, this happens. So, imagine that you have a car where you have the brake pedal, the clutch pedal and the accelerator pedal. In all three pedals you have springs, but what you do not observe is that as you retract any one of these pedals, you do not observe any oscillations in them. Similarly, when you have a door closer and you open the door and you leave it, the door tends to close and it happens without oscillations. So, therefore, you in fact can have a spring which has a tendency to come back to equilibrium position without oscillations. And now, we would like to ask, can we explain these different situations? The first situation being that the spring when given a displacement in its mass keeps oscillating, then a second situation where it does not oscillate, and in fact, there can be a third situation. For example, in a lot of Bourdon tubes for measurement of pressure, you would have observed that the gauge is fitted with oil, and that is because the system has a tendency to oscillate, to vibrate, and to suppress those vibrations oil is put. So, that it is a viscous damping effect which we want to put in there. And in all these three cases, the governing equation remains the same. It is a second order ODE which can be converted to a set of two first order ODEs, and therefore, we have a system which is second order. So, now what we want to know or understand in this lecture is what are the different conditions under which the system will behave differently, and what all are the possibilities which the system can sample. So, we have here a spring mass system. So, this is the spring, and a spring is characterized by the spring constant. So, we have the linear spring which is characterized by the spring constant k, and it is fitted with a mass m such that the motion is confined only along the direction of the axis of the spring, and the system is assumed to have no friction. So, there is no friction here when the mass moves on the fixed surface, and the governing dynamics can be obtained using simple Newtonian balance, which is the second law of Newton's second law, force balance, and this is the balance equation m d 2 x by dt squared plus k x is equal to 0. and we call such a system as free undamped system. Well, I will let you know what is the meaning of undamped, it will become clear a little later, but the meaning of free is that if I give a displacement to the mass in one particular direction and I leave the system to equilibrate, then after leaving the system to equilibrate I am not providing the system with any external force. So, that is why it is called free. I am not supplying the system with any external force except for giving a displacement to the system which takes the system away from equilibrium. So, this is a free undamped system, and then you as I made a mention for the case of Bourdon tube, you can have viscous damping, you can put additional force on the system to make it damped. So, what is the meaning of damping? Let us now define what damping is. Well, you have a spring and it is supposed to, we expect it to oscillate, we expect vibrations in the system. So, there would be oscillatory behavior in the system, and if the system does oscillate with a constant amplitude at a constant frequency, then you say that the system is undamped. So, you have certain amplitude here, let us say this is A, and in the second cycle again if it is A and so on, then you say that it is undamped system. On the other hand, you can have a case where you give the displacement and the oscillations take place such that subsequent amplitudes A1, A2 are such that A2 is less than A1 and so on. The amplitudes of oscillations keep on reducing with time. Such cases are called free vibration with damping, free vibration because you are not providing the system with any external force. So, let us see if we can analyze the dynamics of this system. What we want to know is this: if we can convert the dynamical equations into matrix equations, we have a second order dynamical equation, and we learned that it is possible to convert them to two first order linear ODEs. We will see whether that is possible in this case also, and once we do that, what are the equilibrium solutions, can we develop the phase portraits and comment upon the stability and the effect of various parameters. So, let us see what is the governing equation for, in fact, for the two cases we have m d2x by dt squared plus kx is equal to 0. This is my first equation, and let me convert it to a matrix equation. For that, I will assume dx by dt as y. If this is the case, then my equation becomes m dy by dt plus kx is equal to 0. So, what I can do is I can rewrite equation 1 as dx by dt is equal to 0 times x plus 1 time y, and I can write the second equation 2 as dy by dt is equal to minus of k pi m x plus 0 times y. So, I have converted my second order equation to two first order equations, and how will I convert it to a matrix equation? I can write d by dt of my dynamical variable x y, d by dt of x y is equal to the matrix which will be 0 1 minus k by m 0 times the dynamical variable x y again. So, I have converted my equation to a matrix equation. Let us see if I can do this for the second equation. So, my second equation was m d2 x by dt squared plus c dx by dt plus k x is equal to 0. I will assume dx by dt as y, which means I have m dy by dt plus c y plus k x is equal to 0. So, I can write equation 1 as dx by dt is equal to 0 times x plus 1 time y, and dy by dt as minus k by m x minus c by m y, which will put me in a position to convert this set of equations to a single matrix equation, which is d by dt of x y is equal to the matrix 0 1 minus k by m minus c by m times x y. Okay. So, now if I compare this equation and contrast it with the previous equation, which is d by dx of x y is equal to 0 1 minus k by m 0 x y, then I will see that the functional form of the two equations is identical. The equations are of the form a d by dt of the vector x under bar is equal to a double under bar the matrix multiplied by the vector x again x under bar, but the two matrices in the two cases are different, and we saw that yesterday that we can analyze the matrix and correspondingly depending upon the eigenvectors and the eigenvalues of the matrices, we will get different behaviors. So, this is what we want to do today. So, let us see, let us consider the first case. So, my equation is m d2 x by dt squared plus k x is equal to 0, and I have converted this equation to d by dt of x y. This is going to be equal to 0 1 minus k by m 0 x y. Okay. So, now what I need to do is I need to determine the eigenvalues of this system and corresponding eigenvectors. So, I have the eigenvalues and eigenvectors ready with me. So, let me just write them down. I have lambda 1, which is the first eigenvalue, this is equal to minus I root over k by m, and the corresponding eigenvector is I root over m by k 1, and my second eigenvalue is obviously I root over k by m, and the corresponding eigenvector is minus I root over m by k 1. I leave this as an exercise for you to make sure that this is what you also get by solving it by hand or by any other method. So, if these are the eigenvalues and eigenvectors, then what would be our solution? From yesterday's lecture, we know that the solution would be C 1 e to the power minus I root over k by m t multiplied by I root over m by k 1 plus C 2 e to the power I root over k by m t multiplied by the corresponding eigenvector minus I root over m by k 1. And since x is the displacement and y is dx by dt, which is the gradient of the displacement or derivative, I am just at this point of time interested in knowing the dynamics of the system. So, I am just interested in knowing the evolution of x with time, right. So, from this equation I can write x of t is equal to C 1 e to the power minus I root over k by m t multiplied by I root over m by k plus C 2 e to the power I into k by m t multiplied by minus I root over m by k. This is my solution. Well, this is a solution, but this is not really very elegant and it does not tell me anything physical about the system. So, let me do one thing, let me try to make the solution a little more elegant. So, what I will do is I will convert i's to cosines and sines. Okay. So, what I can do is this, I can write x of t is equal to C 1. Now, I will convert e to the power minus I root over k by m t to sines and cosines, and this will become cos root over k by m t plus I sin root over k by m t multiplied by I root over m by k plus C 2 e to the power I root over k by m t. Okay, so, there is one correction, this will be minus, this will be minus. So, this term would be cos root over k by m t plus I sin root over k by m t, everything multiplied by minus I root over m by k. Okay. So, this is what has converted my exponential of I to sines and cosines. Still the solution is not very elegant. So, I will do further rearrangement. What I will do is I will take this part and this part together with corresponding multiplication here. No, in fact, I will take yes, this part and this part, and then I will take this part and this part together. So, when you take the real part and imaginary part together, then what you would get is x of t, which is imaginary part times I plus real part. Okay. And then we know that imaginary part is a solution and the real part itself again is a solution. Okay. So, imaginary part and real part together are solutions. So, when you would work that out, what you would get is that x of t can be written as a linear combination of the imaginary part. So, let us call it as C 1 times sine of a t plus C 2 times cos of a t. Okay. So, this will be the solution of your dynamical system. Now, C 1, C 2 and A would be expressed in terms of the parameters of the system. I am not here really worried about the exact expression, because I want to know the qualitative dynamics of the system. And what I see from this functional form is that x of t would vary as C 1 some multiplicative constant, which would be in terms of the parameters of the system, times sine a t, a again would be in terms of the parameters of the system, plus C 2 a multiplicative constant times another function which is cos, and that again would be cos a t, would where a would again be the function of the parameters of the system. Okay. So, now what we want to know is that if this is the functional form, how would the system behave. So, let us look into that. So, let me punch in the values here. F of x is equal to C 1 sin a x plus C 2 cos a x. Okay. I see this behavior, but let me do a further diagnosis. This itself is very clear, but let me first make C 2 0. Okay. So, when C 2 is 0, you have a pure sinusoidal behavior, okay, and you can see this this particular behavior to continue in time, pure sine. Then I will make C 1 some non-zero value and C 1 as a 0 value and C 2 some non-zero value, and you see some you see a pure cosine curve. And when you have C 1 and C 2 both, you have an effect from both sine as well as cosine, and what you see is that it does not matter what C 1 and C 2 are. What the characteristic feature of this system is that you have oscillations which are sustained. First feature is that the oscillations are sustained. You do not see any behavior where the oscillations do not sustain. Secondly, what about the magnitude of oscillations? You will see here that in all the cases the magnitude of oscillations, for example, the magnitude here is 2.23, here also it is 2.23, here also it is 2.23 and so on. So, as you go further in time, irrespective of what time has been reached, you always see the same amplitude of the system, and that is why we call the system as, if you noticed here, undamped system. So, the system is called undamped because there is no damping. So, if I have a vibration or oscillation of certain magnitude, then in time this magnitude is going to continue with the same amplitude. So, therefore, there is no damping in the system. First point, there is no damping, and second point is that there is no seizure of the oscillations at all, the oscillations continue. Okay. So, therefore, what we saw here is that you have solutions of the form x of t which is equal to C 1 sin 80 plus C 2 cos 80. Okay. And the solutions look like this. They have same sustained amplitude. But now, in this the x axis is t, the y axis is x of t, and if I want to know what would be the corresponding phase portrait for such a system, then what am I going what will I get? Well, I found out that both the eigen values are purely imaginary. Okay. And what kind of phase portrait do I make when both the eigenvalues are purely imaginary? Well, I can do this, I can make here x, for the current case it would be y, and if I remember what I learned yesterday, the phase portrait would be a center phase portrait. Now, here you have x versus y in the phase portrait, in the solution you have t versus x. So, is there a correspondence between the two, or do they match? Well, it is not very difficult to see. As I said, what is going to happen is that you will circle around these values in time. So, therefore, what is going to happen is that the arrow of time is going to be made something like this, right. So, imagine that I start from this value here at which x is equal to 0, and this corresponds to this, x is equal to 0. Now, my value of x is increasing and it reaches a maxima, right, with time. This is the arrow of time, that is what I see here also. I go and reach a maxima. Once I reach a maxima, the value of x starts decreasing, it reaches a minimum value. Well, that happens here, and then what happens is it in fact it reaches the value 0, not minimum value, it reaches the value 0, and then my time continues here. Now, I have negative x here, in fact I am going to negative x and I am going to the minimum value, this is the minimum value of x, and then I continue here, I again go to x is equal to 0, and once I reach this, when I complete one circle in the phase portrait, I complete one oscillation, and then when I start the second circle, I keep on repeating the same values, right, the same values keep on repeating, and therefore, here also I keep on repeating the same values without changing the amplitude or any of the values in the subsequent cycle, and therefore, the oscillations would continue indefinitely, forever, and in the phase portrait about the center your circle, the point will keep on and circling around and giving you the same value over and again. Now, the only point which is left for us to discuss in this particular problem is that what is the equilibrium solution. We did not worry about the equilibrium solution till now. So, we had the equation d by dt of x y is equal to 0 1 minus k by m 0 x y, and what is going to happen when the system reaches equilibrium. So, the equilibrium solution will be given by the 0 vector. This is important. Okay. Since I have a dynamical vector, the equilibrium solution would be a 0 vector, which means that all the components of the vector would be 0. So, I simply need to solve this 0 1 minus k by m 0 x y is equal to 0 0, which very simply gives me x equilibrium y equilibrium as 0 0. And again, does it physically make any meaning? Yes, well, it does. What is the equilibrium position if you have a spring? So, I have a spring and I have a mass and I give a small. So, this is the, let us say this is the equilibrium position, x equilibrium. So, I give a positive displacement to the system has a tendency to come back here. I give a negative displacement, which means I compress the spring, the system has a tendency to come back again to the equilibrium position. So, equilibrium position here means that the displacement defined with respect to this particular point, which you call as the equilibrium point, is simply 0. You define that point as the equilibrium point, or you also call it as unstretched. So, the coordinate corresponding to the unstretched length of the spring. So, this was the case when you have undamped system. So, undamped free, undamped free oscillations. What were the features? The magnitudes or magnitude of oscillation do not change with time, they sustain. In the next lecture, we will see that it can happen that with time the magnitudes of oscillation may change, or there may be no oscillations at all. Under what conditions will it happen? We will take this up in the next lecture. Thank you.